Today we're going to talk about three more laws. We talked about Dalton's law, partial pressures yesterday. Today we're going to talk about three more: Charles' law, Boyle's law, and Avogadro's principle. All of these have a volume component associated with it. The first one we're going to talk about, and actually all my demos after we turn the lights on, are related to this first one. It's Charles' law, which is a temperature-volume relationship. Now, we talked yesterday about what happens to the particles as we heat them up. What happens to the gas particles as we heat them up? Do they slow down or they speed up? So they speed up, which also means if they're speeding up, they actually take up a larger volume. What we're going to do today is you're going to look at a demo or a couple demos, if this thing warms up enough, where I'll actually cause the gas particles, just the air that we're breathing right now, to actually heat them up and then cool them down really quickly. And you'll see something pretty crazy. But generally speaking, as we increase the temperature, we'll increase the volume. As we decrease the temperature, we'll decrease the volume. And that's directly proportional. Also, with this, we have to use the Kelvin scale. Because again, we can't have what's called a negative volume. So with the Kelvin scale, that gives us the opportunity to only have positive values. Because Kelvin starts where? Zero. At zero and only goes up. And here's a nice little graphic that you have in your notes that shows the directly proportional relationship. As the temperature increases, so does the volume. Notice that in this graphic here, there are the same number of particles, but as the temperature increases, they're moving a little more quickly. They exert more pressure, so it's able to have a little more pressure, which increases the volume. We'll do that once we turn the lights back on. And here's a nice picture. I know that you guys have black and white images in your It's a railroad car tanker. And what happened was, they usually carry some type of liquid in there. I don't know what type of liquids they carry within it. But there's a crew of guys got in there to steam clean the tanker car out. And again, using hot water. There's pressure valves on the side of these things, so in case the pressure builds up, the pressure can be let out. What these guys, or gals, I don't know who did it, got in there and steam cleaned it. Evidently it's pretty cool outside. As they finished the job, it was still pretty warm inside, which had the warm water and the warm vapor. They left, sealed it up, closed off the pressure valves, and based on Charles' law, as the gas is cooled, what happens to the volume of that gas? It gets smaller. Well, if the volume of a gas gets smaller, so does the pressure. The pressure will be reduced. So what happened was the atmosphere actually just stayed the same, but the pressure inside the tanker got smaller as the gas got smaller, and the atmosphere just crushed that can, or crushed the tank. And we'll see that with these. Now the thing was, it's not a slow crush. Okay? In other words, this didn't take like hours to do. It's not like, whoa, look at that. I mean, it was, once that gas started to cool down, that tanker went boom, quick, and you'll see how quick with the demo. But this is showing just different pictures of how this thing got crushed, and that was all because of the atmosphere. We'll use for the first one, or Charles' law, looks something like this. It's a volume temperature relationship where you have V1 over T1, and the ones represent the initial set of conditions, is equal to V2 over T2, okay? And the 2's represent your final set of conditions. We also could write this as T1 over V1. Just depends on what variables we are looking for. Oops, don't make a gamma. Okay? So the equation can be written either way, all right? Depending on what variable you're actually solving for, we want to make sure that that variable is on top, or in the numerator. Okay? So, in this problem here, everybody have that written down at once. I'm going to zap that here. The question states, says a sample of gas occupies a volume of 100 centimeters at a temperature of 200 Kelvin. The question asks, what volume would this gas occupy at a temperature of 150 Kelvin? And it says that the pressure and the amount of gas doesn't change. Here's what I would suggest. When you see problems like this, we'll put the appropriate, let's identify the variables before we begin. So in other words, we have a sample gas with a volume. That's our initial volume, V1. At a temperature T1. Question asks, what volume? So V2, question mark. Would this gas occupy at a temperature of 150? So T2. Okay, so we have our four variables. I'll always give you three, you just solve for the unknown. Now, you saw the equation where it was V1 over T1 is equal to V2 over T2. Do we want to use that equation, or do we want to use T1 over V1 is equal to T2 over V2? Which one should we use? Who should be on top? V2. So we should make sure that we use the equation that has V on top. So you will use this equation, and we're going to solve for V2. And we need to do this before we start punching numbers in. We don't cross multiply in here. So we're going to multiply T2 on both sides. So the equation looks like this. V2 is equal to V1 times T2 over T1. Do that before you throw any numbers in. Okay. Once you have that, now it's easy. Just go back to the problem, see where you mark your variables, plug them in, have fun. Okay, so V1 is 100 centimeters. And here we don't have to do any conversions because the temperature's in kelvins, and this is a volume unit that we can use, so we'll just leave it. But if you don't go and mark your variables as T1, T2, you might flip these. You might stick 200 on top. Don't do it. Okay, that's why we want to label it and make sure that we show this before we do it. So we'll have 150 on top. Oh, yeah, KPA. Or sorry, Kelvin. And then 200 Kelvin on the bottom. Okay. What should my unit be when I finish? Centimeters cubed, which is 75 centimeters cubed. So again, the minimum I want to see is right here. Now you might say, why can't we just cross multiply? Well, next week we're going to have up to about 8 variables that we'll be rearranging. So I want to make sure that you know how to rearrange the variables, and it's just that simple. If it's in the numerator and we need it on the other side, move it down to the denominator once you cross the equal sign. And vice versa. If it's in the denominator, we need it on the other side, multiply it on both sides, it goes in the numerator. So show the variables before you plug in the values. Okay. The next practice problem, number 7. It says, if a sample of gas occupies a volume, there's V1, of 0.325 liters at a temperature, there's T1, of 30 degrees Celsius, what temperature? 2, there we go. We can edit that very well. Will the gas of the volume, will the gas be, what temperature will the gas be at the volume change? Wow. So V2. And the pressure and the amount of gas do not change. Now, looking at this problem, we know that we have a V1, T1 situation, but we do have an interesting situation where we have 0.325 liters and 200 milliliters. We have to have our volumes the same. So do you want to convert to liters or leave it as milliliters?
A liter.
Okay, we'll go to liters. Now, 200 milliliters, and again, you don't necessarily have to show this, but be sure you know how to do this. So 0.2 liters. Temperature, we cannot work in degrees Celsius. We got to get that to Kelvin. So what do? So 30 plus 273, good. So that equals 303 Kelvin. Okay. Make sure that you have, for your volumes or your temperatures or whatever, well, temperatures have to be in Kelvin, but your volumes or your number of moles, we'll talk about that here in a second. Make sure they're the same. All right, so we're looking for T2. So what equation do we want to use? T1 over V1 or T2 over V1? Or T1 over V1 or V1 over T1? Good, so we'll start with T1 over V1 is equal to T2 over V2. And since we're looking for T2, we're going to multiply V2 on both sides. So now we've got T2 is equal to T1 times V2 over V1. And we've already got everything ready to go, so make it happen. We have 303 Kelvin. And V2 is, we left it as milliliters. Oh no, we changed it to liters, sorry. So 0.2 liters over 0.325 liters. And whatever that is, 186. good on that? Boyle's law is a pressure-volume relationship, and yeah, sometimes the temperature does change, but sometimes it doesn't change. And this is unlike the temperature. As the temperature increases, the volume increases. Well, in this case here, if I take a gas and I actually compress it into a smaller volume, what do you think is going to happen to the pressure? Goes up. So it's inversely related. So as the pressure goes up, that means the volume goes down. Because what we're doing is we're pushing those particles closer and closer together, and it's all about the collisions. So if you give it a lot of room to move around, and I mean it, the gases, if you give it a lot of room to move around, it won't make as many collisions. But if you compress that gas, it's able to bounce off more often and cause the pressure to increase. So the inverse proportionality. Pressure goes up, volume went down. If the volume goes up, the pressure goes down. And we'll do some problems with that as well. Okay. And I know I had the equations on here, but I'll save that until we actually turn the lights on. Okay. Everybody get the blanks there? This is a pretty quick lecture. And then I have another picture here showing how as the piston, as it gets smaller, the volume gets smaller, those particles are able to collide more often. And no, gas particles are not doing. The equation, we already talked about it, so it's P1 V1 is equal to P2 V2. So initial pressure, initial volume is equal to the final pressure times the final volume. All right, so number 8 says a sample gas has a volume, P1, of 100 centimeters cubed when the pressure, P1, is at 150 kilopascals. Question is, what is the volume, V2, of this gas when the pressure is increased to P2, 200 kilopascals, and it says the temperature and amount of gas remain the same. So which variable are we solving for here?
Volume.
Yeah, we're looking for the final volume. So that means we're going to divide P2 on both sides. So my equation is, our final volume is equal to P1 V1 over P2. Now, as a heads up, to make sure that your units and that you're putting things in correctly, the variable you're looking for should have a representative on top or in the numerator. Okay? If you inverted that somehow, some way, and you had your representative for the variable you're solving for is on the bottom, you messed up. Because we need to have that unit on top, obviously. So when the pressures cancel out, we're left with a volume unit. So just as a heads up. Did you say something else? I'm sorry. Okay. So we'll go ahead and plug in what we know. So our P1 is 150, and that's kilopascals. Our volume is 100. And that's over our final pressure, which is 200. So I think that gives you 75 kilopascals. Oh, sorry, centimeters. My bad. Thank you. Can you see through him?
Yeah. He's not even in the way.
Super. And another one. Number 9 says a sample of gas has a volume of 330 milliliters. So that's our V1. When the pressure is at 760 P1 millimeters of mercury. What is the final pressure? So question mark P2, and it wants it in atmospheres when the volume is changed to 5.5 liters. So V2. Okay. Now before we begin, we have units all over the place here. For your volume, do you want it in liters or milliliters? Liters, and it doesn't matter, just as long as you convert both. So if you're going to leave it in liters, make sure you convert that. If you're going to leave it in milliliters, make sure you change that. So 330 milliliters, and you don't have to show this, but be sure you can do it correctly. It should be 0.33. Okay, so that's our new volume. It wants the pressure in atmospheres. So do you want to change the pressure now or later?
Now.
Now? Okay. So we can change it now from 760 millimeters of mercury. Convert the millimeters of mercury to kilopascals. Whoa, let's get some room there. many millimeters of mercury are there in 1 kilopascal? Good, 7.501. And then 101.325 kilopascals for every atmosphere. You're gonna love this. That's 1 atmosphere. Okay. So good call changing that. Now you can do that at the beginning or at the end. Obviously it'll give you a different value if you do it at the end. Alright, so our pressure now is equal to 1 atmosphere. I'm going to erase that. Does anybody still need that? It'll be on the video. Alright, so we have P1, V1 is equal to P2, V2. So what variable are we looking for?
You're looking for that one.
P2. So we'll divide V2 on both sides. So P2 is equal to P1 times V1 over V2. And again, our pressure that we already converted wisely is 1 atmosphere. Our V1, where's our V1? It's right there. We change that to liters, so 0.33 liters. And our final volume is 5.5. Anybody get a number for that? 6? So 0.06 atmospheres. All right, Avogadro's principle. Probably the easiest way to describe Avogadro's principle, and this is going to sound really dumb, but this guy gets credit for it. As you blow up a balloon, okay, you put air in a balloon, what happens? It gets bigger. Okay, so here's Avogadro's principle. You add more moles of particles, the volume gets larger. You reduce the number of particles, the volume gets smaller. Isn't that brilliant? Something like that. Yeah, something like that. All right. Now, these are in your notes. We'll go over these when we work out the problems. And we already did this one yesterday. The last practice problem says a sample hydrogen gas has a volume of 630. So there's our V1. When the sample contains 3 moles, and again, I love this, M1, number of moles, awesome. Brilliant, number of moles. What is the volume? So question mark V2 of this gas in centimeters cubed when the sample is reduced to a number of 1.75 moles, so N2. Okay. So the equation again is V1 over N1 is equal to V2 over N2, or you could have the N's on top and the V's on the bottom. Which should we do?
The second one.
So have the volume on top?
Yeah.
So good, we'll start off with V1 over N1 and V2 over N2. Okay. So, since we're looking for the final volume, we'll multiply N2 on both sides. So V2 is equal to V1 N2 divided by N1. And again, there's that situation where you could accidentally put the wrong N's in the wrong spot. So we have our pressure, our volume, which is at 630 centimeters, which is okay. We'll leave it at that. Our N2 is over here, the 1.75. And that's moles. And that's divided by 3 moles. Which equals 368. You're close on the last one. Okay? All right. Think you can do this?
No.
Yeah. Pretty easy. So what this is, okay, let's start over. Both of these examples that I'm about to demonstrate deal with Charles' law, and this can has been sitting in really hot water for a while. Get out. Really hot.
Craig, don't we have gloves?
Whoa.
All right, so stay up there.
I just noticed.
That's part of being next next to it. All right, so what I'm doing is I'm heating up the gas inside the can, and you can see that it's really getting excited. This I had some ice in, took it out, so it's a little cooler. So the gas inside is actually pretty warm. Would you agree? Mm-hmm. So if I take this and I place it in the cooler water, what's going to happen to the temperature of the gas inside?
It's gonna go down.
It's going to cool, which is going to cause the can to do what?
Crush.
Crush. So
Whoa. Whoa. Wow.
that was nice. It was like crap. But I'm going to remove it for a moment without burning myself. Key is not to burn yourself. Trying to go fast here. Shut up. This will be, yes, it is very hot. It's coming off. There we go. Got it. All right. So obviously you can tell it's very warm. Another thing, warm, hot, whatever. Actually, this is starting to get a little excited there. So what I'm going to ask you is, let's put that in there, since I haven't learned my lesson. The particles are the gas that's in the can. There are some gases in there, because you can tell because you can hear the can dancing. Okay. So are the particles in there moving around pretty quickly or not?
Yes.
All right. Now, this goes fast. Okay. So don't. Can you see here? Oh, sorry. Yeah. All right. So again, this is our atmosphere that we're experiencing right now. Woo! Wasn't that exciting? All right, this is an example of a multi-view shot. And what we can do with these multi-view shots is we can edit these so that we can get one of the best views. Maybe one view doesn't work out really well, but the other camera on here is I've got two round bottom flasks that are heated up, and I've got some water with some food coloring in there, and we're going to do a pretty cool demo here. This is a gas property, or a nice little demo to help demonstrate what happens when you take a very hot gas, and I don't know if you can see the steam that's coming off of here. Try to get a dark background here. I don't know if you can see the steam that's coming off from behind there, okay, from that camera, or if you can see it from behind that camera. So there's a lot of steam coming out of these round bottom flasks, and they're really hot, ready to go. If I had these without these openings here, these things would blow up because the pressure would get so great within. But what I'm going to do with this big one here so I don't accidentally knock it off. Set it right there for just a moment. And we're going to focus on this small one. And what's nice is this is also going to give us some editing capabilities we can discuss. You can look at the raw footage and then notice how I edit some of this information out. Alright, so here, what I want to explain is we've got water. That's a liquid that's boiling. In other words, it's changing from a liquid to a gas. As it changes to a gas, that gas is being heated inside of the round bottom flask as well. As it's being heated, it's building up pressure, a lot of pressure. I mean, it's pushing quite a bit. I don't know if I can get a piece of paper to kind of demonstrate. So I'm not going to put my hand on it, but it makes a nice little hissing sound as it's coming out. Okay, so we never want to put our hand over that because steam is warmer than boiling water. So that temperature is above the boiling point, so it's hot. Also, what that means is there's a lot of gases that are inside these round bottom flask containers. So what I'm going to do is I'm going to cool this gas down quickly. As I cool it down, you're going to see something pretty cool take place. And what I've got in the beaker here to my left is some more water with some food coloring, and I put food coloring in there mainly so that you could see what's happening. So I'm going to cool this gas. As the gas gets cooled, something very, very cool is going to take place. I'm going to try to keep my hand out of the way so you can see what's happening here. I'm going to apologize in advance for the noise that it's about to make. Alright, so now what's happening is the gas is starting to cool. As a gas cools, it becomes compressed. As it's compressing, it starts to compress the other gases that are inside of the container. So it rapidly pulls the water in, causing a vacuum. And it's going to actually compress that gas so much that it's going to fill this container completely up with water. Here we go. Alright, so now what's happening is the gas is starting to cool. As a gas cools, it becomes compressed. As it's compressing, it starts to compress the other gases that are inside of the container. So it rapidly pulls the water in, causing a vacuum. And it's going to actually compress that gas so much that it's going to fill this container completely up with water. Now, if you've ever had a chemistry class, this is actually a temperature and a volume relationship. The bubble that's on top here, I don't know if you can see that bubble that's on top, that's the final volume of this gas. The gas used to be this same volume, because it's a bigger one. Kids usually like the bigger one anyway. So what I'm going to do is I'm going to pour this water back in there. We're going to do it again with the big one. Now, since I've already preheated that, it's not going to take as long for it to heat back up. So as that's heating up, I start to see some steam coming out. Now it's spitting out already. We'll let it warm up a little bit. We'll give it a chance to let all the gases warm. Right now, boom, it's already going. So it did not take too long to get that water back into the phase where it needs to change from a liquid to a gas. Alright, so as that's building up pressure inside, we're going to cool the gas. As we cool a gas, it compresses. That's the same thing that happens if you were to, well, we all know about what happens if you leave a can of Coke in your car on a hot summer day. The pressure inside builds up and it explodes. Well, this is a reverse. This is an inversion. It's causing a pressure which is drawing everything inside that it can without collapsing the container. Now, if I cooled the gas down, it would suck air in, but that's no fun to watch. Alright, so let's get this guy. Okay. Alright, here we go. Let's turn the power off on that. Okay. So again, as that starts to cool within, I can see the water slowly lifting up. And now as it cools the gases inside, we see a tremendous, how quickly this gas changes or is compressed. And as it's compressed, it changes into a vacuum, drawing that liquid in quicker and quicker. Hopefully I'm not going to, oh, good. So it's going to try to draw it all in until that container is completely filled. Try to get my hand out of the way. And not pull it out of the liquid. Come on, get it in there. So it's still going, still going, still going, still going. It's trying to get it all. Ah, it's completely full. Okay. Alright, here we go. Let's turn the power off on that. Okay. So again, as that starts to cool within, I can see the water slowly lifting up. And now as it cools the gases inside, we see a tremendous, how quickly this gas changes or is compressed. And as it's compressed, it changes into a vacuum, drawing that liquid in quicker and quicker. Hopefully I'm not going to, oh, good. So it's going to try to draw it all in until that container is completely filled. Try to get my hand out of the way. And not pull it out of the liquid. Come on, get it in there. So still going, still going, still going, still going. It's trying to get it all. Ah, it's completely full. Must have been from the volume from the other container. Alright, so that concludes our demo for cooling of a gas. Pretty neat, huh?